Good morning, everybody. This is quite a change. So, I am not able to be there with you physically right now, but I am here with you virtually and in spirit. We are going to finish up our Unit 9 in general notes. After we finish these notes, as I mentioned last class, we are done with notes for the year. The rest of the year is just projects, Khan Academy, and retakes of projects. That is it. We are home free. However, I do want us to participate with this one. Here's the deal. This page here is going to show you exactly how to do part 2 of your project. So we really need to focus in. With that said, let me read the prompt. Who will score more points? UNC or Kansas? So, who scores more points per game? UNC or Kansas? A random sample of 33 games from 2021, I think it should say from the year 2021, showed a mean of 75.673 points per game and a standard deviation of 5.225 for UNC. This is what we're used to seeing. We did this in the last couple of activities. For instance, the last activity we did was how many points will MSU average? And it gave us the same data, basically. They said, hey, 6 games, average number of points. Here's our sample mean. Here's our standard deviation. So far, so good. So far, so similar. However, we're not just talking about UNC now, we're talking about Kansas. A random sample of only 30 games revealed a mean of 81.967 points per game and a standard deviation of 11.115 for Kansas. And the question is, do these data, I should say data points, give convincing evidence of a difference in the population means at the alpha equals 0.05 significance level? Now, I want you to pay close attention to convincing evidence of a difference. What we're looking for here is not, oh, let's do some test statistics, let's see if they're within the mean that we expect them to be. We're trying to see if they're close enough to each other to see if there's a difference. Before we get started, let's make some predictions. I want one person to raise their hand, and based on this data for UNC and for Kansas, what do you think? Is there a significant difference between the points per game? And why? Why do you say so? Or why not? Pause the video here and check in. Hopefully you had a chance to discuss. Otherwise, I'll sound like an idiot, just sort of pausing there for about 15 seconds. So, let's figure it out together. First things first, as always, we've got to state our parameter, statistic, hypotheses, and significance level. Well, right off the bat, we are going with a significance level, not a confidence interval. So we are going to be doing something kind of like we did with the Flint and the water bottles. The significance level is based on your alpha. So that's going to be 5%, because we have an alpha value of 0.05. It's important to note, though, are we looking for one team to be 5% bigger, 5% smaller? It doesn't matter. It just has to be a 5% difference overall. Keep this in mind. Let's talk about the parameter. Obviously, we're talking about the means here. We're talking about the averages. But what can we use to represent these two averages? Well, we're obviously going to need 2 variables. What I'm going to do is this. I'm going to assign mu1, and I'm going to say that mu1 represents UNC. This is the true mean of UNC's games. To find the true difference between them, though, what does difference mean? Subtraction. So, we're going to subtract mu2. Pokemon reference. We're going to subtract this, which is going to represent the games that Kansas played, the true mean of all of Kansas's games. So what have we just done? This, our parameter, is the true mean difference. The true mean difference, or the true difference in means. That's what we're really looking for. Next up, let's go to our statistic. Remember, the statistic is the much more specific sample measurement that we got. So, we did get some means from our data. We got two of them. We've got a mean from UNC, which we're going to call x bar 1, or x1 bar, technically. But we're still trying to find the difference. So, we're going to subtract x2 bar. Well, the difference between the parameter and the statistic is the parameter is a general goal. The parameter is saying, hey, when we're done with this, we're going to figure out this. That's what we're going to figure out. The statistic is what we already know. So we should already know what the difference in the means are. Well, what is the difference in the means? The mean of UNC is 75.673. And I'm going to stop here because I want you to figure out the rest. Can you figure out what x2 bar represents, and can you find the statistic by the end of it? Pause the video and try it out. Again, hopefully you pause the video. The mean for x bar 2 is 81.967. So, when we subtract these two, we should actually get a pretty reasonable statistic. The statistic is there's only a difference of 6.294 between these two. Once again, that is 6.294. Of course, you would get a negative number, wouldn't you? Turns out, don't matter. It really does not matter. Because we're just trying to find the difference between the two, you can kind of take the absolute value and just say, get your positive version. All right, now on to the hypotheses. There's always two. You've got H0 and HA. Ho-ha. What does H0 represent? I'll pause the video here, see what we can come up with. H0 represents the null hypothesis. In other words, what we guess is going to happen if nothing is abnormal. It's sort of like the standard situation. So what's the standard situation we predict here? Well, we predict that there's not really going to be much of a difference. It's truly. We're trying to find evidence that there's a difference. So, what we're saying right now is, we don't think there is one. The null hypothesis is that mu1 minus mu2 equals 0. There is no difference. But the alternative hypothesis, the alternative is what happens in the other case. Mu1 minus mu2 is not 0. All right, we have just done the state step. Now it is time to plan. We have a name for this type of test that we're running. It is called a two-sample t-test two sample test for the difference in means, which we're going to call mu1 minus mu2. This is why I said this is all of part 2. This is literally what we're learning to do. And now for everybody's favorite part, we need to check the conditions. There are 2 conditions we have to follow, and I know it's been a weekend, so can we remember them? Again, I'm going to have to ask you to pause the video until we can get those 2 conditions and get them confirmed. Hopefully we were able to check these conditions. This is something that we should definitely be able to do after our project. But the 2 conditions are whether or not it's random and whether or not it's normal. Why is it random? Well, because the problem says so. It's a random sample here, and it's a random sample here. Random's good. But why is it normal? Well, to find if something is normal, it all comes back to a couple of things. It doesn't say it's normal in the problem, so we can't go to that. However, our sample sizes are relatively big. In fact, n has to be greater than or equal to 30 in order for it to happen. What are both of our sample sizes? Well, we have 33 games from UNC, so 33 is bigger than or equal to 30. And we have 30 games from Kansas, 30 is greater than or equal to 30. We've got 2 more check marks. We are all good. We did not need to do hillbilly math here. And the hillbilly math would be saying, hey, we can kind of approximate it as normal, sort of, as long as it's not skewed and as long as there aren't any real outliers. We have no way of saying that. We have no way of telling from this data. So we would say, sure, it's normal. From here, now we just have to do. So, first things first, for the mean. The mean that it's asking for here is the mean of the distribution that we are going to make. Again, we are going to make this sampling distribution and then test the significance. So let's start off by actually drawing a picture. We know what this is going to look like. We know it's going to look like a normal curve. But what's in the middle of our normal curve is the real question. Well, it's our desired outcome. It's always going to be our null hypothesis. Our null hypothesis said the difference in means is 0, right? So, for the purposes of this distribution, we're going to call mu 0. The mean of this distribution is going to be right at 0. And what we're really tracking here is the difference between the two. For instance, if we got a number that's different, say by, I don't know, 6.294. Crazy that I said that specific number, right? Well, remember, we are going to use our sample means to tell where or how far we go from our hypothesis. So, 6.294 that we got from our statistic is probably going to be on the higher end of the data. This means there's a difference in scores of like 6.2 or 6.3. But all the way up here, this would be if the mean scores had a difference of 10 points per game, or 20, or 30. And back here would be all the negatives. Well, wait. Remember how before we said the significance level could be 5% higher or 5% lower? We should also account for this lower portion of the curve. So, this is what our distribution is going to look like. The mean was easy. The mean was very easy, in fact, because the mean is just our null hypothesis. However, let's flip back to an earlier lesson where we also did this same thing. Remember how we found the standard deviation? We said the standard deviation of our distribution was going to be the sampling standard deviation divided by the square root of n. Because we've got two sets of data here, it's going to be a teeny tiny bit more complicated than that. In fact, it's going to look a little bit wild. So please bear with me. I'm going to write this up here so we have enough room to do the work down here. But the standard deviation is as follows. Let's make sure we can see that. It's going to be the square root of, oh boy, here we go. Your first standard deviation, so we'll call this one Sx1, squared, this is a new one, we're squaring our standard deviation, divided by n1. This is going to be the sample size of your first set of data, plus Sx bar 2 squared divided by n2, the sampling size of your second set of data. Oh boy, this is going to be a fun one to do. But it's okay, because we just need to plug in our numbers. This is just a formula. It's meant to be plugged in, not toiled over. So what's our first standard deviation? Well, it says we have a standard deviation of 5.225. So let's write in, I'll write this in a different color, 5.225. And remember, we're squaring this. So it's going to be 5.225 squared divided by, what's our sampling size of the first set of data? 33. Plus the same thing all over again for our second set of data. Well, our second set of data has a standard deviation of 11.115, and it has a sampling size of 30. This is a huge calculation to process. What I recommend is taking it literally one chunk at a time. Calculate this down, add them, then square root them. Pause the video here and try it out for yourself. See if your number matches mine. We should have gotten something pretty aesthetically pleasing. 2.22. Technically 2.224 if you want to be, going to significant figures. So 2.224. Hopefully we were able to get that. If not, double check your intermediate calculations. Double check this one, add them up, and square root them. Alright. You thought that was bad. Oh boy. Here comes the general formula for how we actually figure out if the difference is significant or not. Now, this is going to be another big one. The difference of two sets of data is a lot trickier to find than the difference in, or than just to find the difference in one set of data. The general formula, as we learned in our notes, is always going to follow the same format. It's always going to be this. T star equals your statistic minus the null divided by your standard deviation. When you have the difference of two means, it is no different. Our test statistic is equal to our statistic minus the null divided by our standard deviation. Well, we happen to know a lot of these pieces here, unfortunately. Well, fortunately, I should say, sorry. We know this is going to be T star. That's a good start. What is our statistic? Well, it's x1 bar minus x2 bar. And we know what that is, but I'm going to write it out as x1 bar minus x2 bar in parentheses. What's our null? Well, our null is the difference between our true means. mu1 minus mu2. Cool. And our standard deviation, well, we just calculated that, so we don't need to do much work there. All we need to do now is plug it all in. T equals the following. Our statistic was 6.294, as we mentioned before. So it's going to be 6.294 minus our hypothesis, our null hypothesis was that the difference is going to be 0. So we could actually just put minus 0 here. Very nice. That's not always going to be the case. And last but not least, we just calculate our standard deviation. 2.224. Let's find it, everyone. Pause the video, calculate it out. Hopefully, after calculating this out, we should have gotten a pretty satisfying answer. We should have gotten the following. We should have gotten 2.830. So that's our test statistic. Our test statistic is t equals 2.830. Very nice. From here, we need to find our p-value that corresponds to this test statistic. As a reminder, we are going to multiply our values by 2 since we have a two-sided distribution here. Let's go over to our table and see what we can discover. All right. First things first. When it comes to the degrees of freedom, we kind of want to have the most accuracy possible. What this means for us is we are going to use the degrees of freedom that is about halfway between what we have, rounded down. Notice our samples are 30 and 33. We're going to take our statistic at 30. Now, we are going to find the p-value that our test statistic, 2.83, lies between. It's right here. When we scroll up, we take a look at what these two numbers correspond to, and we see they have p-values or probability values of 0.5% and 0.25%, or 0.005 and 0.0025. So let's write those down as our p-values. Our p-values are 0.005 to 0.0025. This is our confidence of where our data lies. But we need to multiply it by 2 because it's a two-sided set of data. So we actually get 0.01, so 1%, to 0.005, half a percent. Well, according to our notes before, our p-value has to be greater than 5%. In order for this to work, we need to be above that 5% threshold. We're in the 1 to 1/2% threshold. So what this is saying is basically this. Hey, if this data really does represent these teams in general, there's like maybe a 1% or a 0.5% chance that your null hypothesis is correct. What we say then is this. We say the following, and you need to write this down word for word, same as in your project. We have convincing evidence because the p-value, p-value is between 0.01 and 0.005. We reject the null. We do not agree with the fact that these two teams have no difference between them. There is a very clear difference between these two teams. Technically, I shortened it here, so I was a little bit of a hypocrite, but we would say we have convincing evidence that there is a difference in the population means at the 0.05 significance level between the two teams because of the p-value, blah, 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 blah. Let's formalize this, everyone. So, in the notes, we are going to write down the following. We've got a couple pieces of information we want to talk about. First things first, our hypotheses. H0, our null hypothesis, is always going to be the difference of our means. And if you're testing a claim about a difference of two means, try and see if there is a difference, you'd put 0. If the problem said, oh, we're pretty sure there's a difference of exactly 22 coconuts, you would put 22 there. That's the null hypothesis. The alternative hypothesis is always going to be the opposite. So the opposite of this is saying, hey, it's not going to equal 0. There is going to be a difference. Now, the formula for t is a little bit tricky to use. So we're going to use the rest of the space to make it. I apologize for this. To find t, we are going to take x1 bar, whoops, see, I'm already messing up on our limited space. x1 bar minus x2 bar minus mu1 minus mu2. Again, this is our statistic, minus our null. And then we did that big thing for our standard deviation, so the standard deviation is going to be the square root, big square root of s, I'll just call it s of 1, not sx bar of 1, but s of 1 squared divided by n1 plus s2 squared divided by n2. This is the formula you are going to use for your project. Finally, when using your degrees of freedom, you're going to use the degrees of freedom closest to what you've got. Sound good? All right, everybody. That's it for the notes today. Good luck on working on your projects. And if you have any questions, let me know.